So what we do today and tomorrow is the second half of talking about quantum computation with magic states. So we have already talked about the computational scheme last time. Today and tomorrow we will talk about the role of Wigner functions in it. We'll talk about what Wigner functions are. So you said last time you didn't have them yet in the quantum optics lecture, so I'll introduce them here, which is a little bit of an odd thing, but anyway, I'll do it. So it's a notion from quantum optics. Basically, the Wigner function is the density matrix represented in a certain basis. Yeah? And then you can attribute some physical meaning to the quantum state in that basis. Namely, whenever the Wigner function dips below zero, then you think there's some truly quantum going on there. And if that doesn't happen, then it's effectively a classical situation, and we will see why this is so. And then there is a rigorous version of that statement that non-negative Wigner function is essentially a classical object or describes a classical object. Yeah, so in quantum computation you can make it rigorous, and that's the purpose of today's lecture and tomorrow's lecture. So precondition, Wigner function negativity as a precondition for quantum speedup. This is what the two lectures are about. And today we are just going to redefine what Wigner function we are talking about, because there's many to choose from. And we will go over the broad outline of the argument, and we'll do the details tomorrow. So there is a reading. So this lecture is based on part of David Gross's thesis on this paper. Yeah, so this is the reading for today and tomorrow. This is background material. So Wouters and company, they defined a whole range or whole class of Wigner function, and Gross picked one of them. And it has particularly nice properties, as we shall see. Okay, so this is the background. This is what we will actually be using, and this is how we will be using it. Okay, so this is a recap of what we talked about last time. Quantum computation with magic states. So remember, it is almost the circuit model, except that you do not have a universal set of gates. And you replace the gates that are missing, namely the non-Clifford gates, by something else, by so-called magic states. And that's what we saw. You can inject magic states and recover the missing unitary gates. And that sounds, at the face of it, a little bit unnecessarily complicated. But from a practical point of view, this is actually how you would do fault-tolerant quantum computation. It's the most efficient way we know how to do it, and we talked about that last time. Okay, but these practicalities don't matter for us right now all that much. So we observe that computational power is shifted from the unitaries to the states that you put in, the magic states. And the question is, what property do these states need to have in order to provide a quantum speedup? Okay, so that's the question. Okay, that was a detail from the recap. So this is the magic state injection circuit that we saw last time. I hope you remember. This is how you replaced the application of a Clifford unitary, or how you did it using Clifford operations only, plus the use of a magic state. That was the whole difference to the circuit model, this state injection circuit. Yeah, but today our question is, which properties do the magic states have? Which properties do they need to have so that they can give you a quantum speedup? And the answer that was given is negativity of their Wigner function. Okay, so there is a theorem. It has been derived in various contexts. I talk about the distinction in a moment, but let me just read the theorem to you. So quantum computation with magic states can have a quantum speedup only if the Wigner function of the initial magic states is negative or takes negative values. It's a function. It doesn't have to be negative everywhere. It just has to take negative values. So if you have that, that doesn't guarantee a speedup. But if you don't have it, that guarantees the absence of a speedup. So negativity in the Wigner function is essential for quantum computation in this model. And this was first described for qubits, not for qubits, but for systems with more levels. And the important thing was that the number of levels had to be odd. Yeah? So even is always tricky, and that's why we have a restricted case for even dimensional systems here. So this is the case for rebits, so just qubits, but real wave function, no complex numbers involved. Okay, about this whole distinction between even and odd, we will talk later. Why this is such a major difference. So we will focus here on the odd dimensional case and then maybe talk a little bit of where the difference comes from. Okay, but we begin with the odd dimensional case. This is the major case for us. It's a lot easier to deal with, as we shall find. So that's the program for today. So what I want to do today is I want to illustrate the result and how it is basically derived. And so there will be lots of details that I will not mention today, and I will discuss them tomorrow. Okay, so now let's talk a little bit about what Wigner functions are. Well, so imagine Hilbert space, say infinite dimensional, a particle moving in space. Yeah? So you have particles can have position and momentum, and that is what a Wigner function, here denoted by W, will depend on. It has a position and momentum coordinate. And why do we have it? Well, it's the closest quantum counterpart to the probability distribution over phase space. So remember classical mechanics, yeah, statistical classical mechanics, so probably some time back. So this little duck here is, I mean, a good approximation to a point in space, and you can throw it. I will not break, but I will not throw it. And so if you throw it, at every moment in time, it has a position, it also has a momentum. Yeah? And you can plot that in phase space. So in phase space, that would be a point. One coordinate per dimension, if it is in higher dimensional space. But anyway, one set of coordinates is for momentum, the other set is for position. So in three-dimensional space, if you will, you have 6 coordinates. Yeah, and a classical system, at any moment, you can, in principle, perfectly well specify by a point in that space, in that phase space. Now you think, yeah, maybe I don't know my initial conditions so well. Maybe my velocity is in this range. Maybe my initial position is in that range. And so that point blurs out into some probability distribution. Yeah? And then supposedly you know your evolution equations well, then that area in phase space, say, it moves about in phase space. But in principle, in classical mechanics, it's possible to have a perfectly sharp distribution, just a point in phase space. And now you want to take that picture to quantum mechanics, and in quantum mechanics, it must fall apart because of the Heisenberg uncertainty relation. You cannot have position and momentum arbitrarily well specified at the same time. So this whole concept of probability function over phase space, that does not straightforwardly apply in quantum mechanics. So you need to think about something else. You have to replace it by something. Okay, and that's what the Wigner function is. The Wigner function is the closest quantum mechanical counterpart to the classical probability distribution over phase space. That's what this thing is. Yeah, it's as close as you can get, but you have to pay a price. The Wigner function can take negative values. It's not a, I mean, you know, negative values, they don't look good for probability. Yeah? You want probabilities to sum to 1, but you also want probabilities to be 0 or positive. If your probability function in quotes dips below 0, then there's something wrong with it. The Wigner function is such a function. It does dip below 0, and that's why it's called quasi-probability. But it has lots of properties that make it otherwise look like a probability function. So to give you an idea of what I mean, there are these marginals. And what a marginal is, you have these quasi-probability function depending on p, that is momentum and position. And you could integrate over position. So you could integrate along a line like this, you fix the momentum and integrate over position. So that would then be intuitively the probability for finding the particle in with a certain momentum, state with a certain momentum p. And that thing, even though the original object, the Wigner function, did dip below 0, these marginals will be fine. They will be proper probability distribution. So this is for the marginal over position. So the momentum marginal is also true for the position marginal. All these will be proper probability distributions, exactly as you expected from quantum mechanics. When you measure the momentum of a particle, you expect to get a probability distribution. When you measure the position of the particle, you expect to get a probability distribution. And that's exactly what you get from the Wigner functions when you take the marginals. I think, even though it doesn't matter for us at all in this class, since I'm throwing around Wigner's name a lot, I should maybe write down the Wigner function, how it is originally defined. And it is defined as you see here. The Wigner function is a function of momentum and position. It represents a density matrix rho. So the Wigner function will always be of a density matrix. Yeah? And it is expressed in this form. So you have the density matrix here. You are sandwiching it between a cat and the bra. So the cat and the bra, they contain the position. You're evaluating the Wigner function at a certain position. So you find these positions here. And you have an integration variable, y, that's also present in this cat and bra. Okay. Yeah. And then you have a phase factor 2, and that contains the momentum point at which you evaluate this Wigner function. Okay, so yeah, so after integration, Wigner function depends on position and momentum. Okay, also an interesting property is that the Wigner function is linear in the density matrix. You see this right here. Also, it is in a one-to-one correspondence. You can start with a density matrix and obtain the corresponding Wigner function, or you can start in a Wigner function and reconstruct the corresponding density matrix. Good. So that's the thing that Wigner introduced almost 100 years ago. Okay, so what we will need is an adaptation of this thing for finite-dimensional Hilbert spaces. So what you see here, you have integration minus infinity to plus infinity. So this is just for ordinary wave function and position space, and that's infinite-dimensional Hilbert spaces. So we want the finite-dimensional counterpart of this. Okay, and that we have yet to define, and that is the PhD thesis of David Gross. In this quantum optics domain, to give you a few examples of what these wobbling things look like. So again, so here you have a Wigner function of a so-called cat state. So let's just quickly see what this is. So this is a superposition, coherent superposition of two coherent states. So coherent states, so by themselves, they are basically what they would look like as a Wigner function are just Gaussian peaks centered around a certain point. what this number alpha is here. It's a complex number, and it denotes, if you would look at the Wigner function of this thing alone, it would be a Gaussian peak centered around that value. But now you look at the Wigner function not of this thing alone, but the superposition of two of them. One located at alpha and one located or centered around minus alpha. And that Wigner function has structure. So it's no longer just a blob, just a peak, but it has these interference effects. Yeah? So you see it go dipping below zero. Okay? And that is an indication of quantumness. Good. Okay, so that's just kind of what Wigner functions look like in quantum optics. And let me give you another example of this. I mean, I should also say, so these images are all from Wikipedia. So let's look at another set of states. So these are Fock states. So these are states of photons, say, with a fixed photon number. So it begins with no photon in it at all, still has a Wigner function, so a properly defined state, and it is a Gaussian. It's a Gaussian centered around zero. Yeah? And then here you see the marginals, marginal probability distributions. I have a Gaussian for position, for the distribution of positions, and a Gaussian for the distribution of momenta. So now, when we go to n equals 1, so now we have one photon here, the Wigner function begins to do crazy stuff. So you see it starts out like a peak up there, but then you actually turn into a dip. So the Wigner function becomes negative at the center. Huh? And still, the marginals are perfectly fine. So the marginals integrated over position and momentum respectively, they are totally proper probability functions. See, where you had the dip in the center and then this rim around that, so that all cancels out such that here at this point, at the central line, you get no probability, but you have probability here and there. Okay. And so, well, it's getting progressively more crazy. So this is a Fock state with 19 photons in it. And you see this very delicate structure over here going up and down, up and down, up and down. And you see that the marginals for position and momentum are still fine. That's that. Yeah? Wigner functions can go negative. Marginals are always fine. So this is the concept of a Wigner function in quantum optics. And if you take a course in that field, you probably will talk quite a bit about Wigner functions. But that is Wigner functions for infinite-dimensional Hilbert spaces, and this is not what we need here in this course. So this is quantum computation, so we need a finite-dimensional counterpart. So Wigner functions for QDITs. The upshot is, and that's what we are going to develop now, the upshot is that this thing, Wigner's original Wigner function, can be adapted quite nicely to finite Hilbert space dimension as long as that finite Hilbert space dimension is odd. If finite Hilbert space dimension becomes even, then all hell breaks loose. And we save that for later, and we will probably not talk about that very much in this course. So we mostly will stay with odd dimension where everything is just fine. Sorry about my handwriting here. So this is just to introduce a new concept, the phase point operator, for which we want to find a counterpart later on in this finite dimensional case that we now care about. Okay, so this is the definition of the Wigner function that we started with, and now we just play a little bit with cyclicity of trace. So we get from here to here. Yeah, so all I've done is I've taken the bra, moved it to the other side, and introduced the trace here, keeping the phase factor. And then I thought, oh, maybe it's a good idea to take the integral inside. So we have the trace is a linear operation. in its argument, so we can take the integration inside. And so now what we have is the expression down here. So we have a normalization factor that maybe doesn't need to concern us very much at this moment, but we have an expression for the Wigner function at some position and some momentum that is some operator constructed in a certain way times rho. And this operator is a function of position we care about and momentum we care about. That's called a phase point operator. So the upshot of this is we can write the Wigner function at a certain position and momentum as the trace of rho, our density matrix, times a phase point operator. And that construction principle we will take over from the infinite dimensional scenario to our finite dimensional scenario. So we will be constructing these phase point operators. Okay, so now let's go to finite dimension. It's not clear why we need this assumption right now, but we will assume that D is odd. We will soon see where we need this assumption. Okay, and so we have a D-dimensional Hilbert space, and we find a basis for it. We would normally call this the computational basis. Now, for that system, just for later we have multiple such systems, but for now we just look at one. For such a system, we will have so-called while operators, and they are just the generalizations of Pauli operators that we saw last time. I mean, when we talked about the stabilizer formalism for qubits. There is just on a similar footing a stabilizer formalism for qubits. It's just the same, except the operators we deal with, the Pauli operators, have different eigenvalues. Okay, good. So there is something that used to be the spin flip operator X, capital X, will now be a shift operator. Yeah? It has this action. So you take any of the states in this basis and you get the one level higher up. Except, well, it's a finite dimension. So when you're already at the top level, you actually go to the bottom level. So this is what the operator X does. And so you also see if you do this D times, you get back to where you started. So that operator raised to the dth power is the identity. Okay, and then you have a counterpart to the phase flip. And so what the phase flip does is it gets you a phase factor. So the state remains the same, but you're getting a phase factor, and that phase depends on where you were. Depends on, well, the larger that number, the larger the phase that you pick up. Okay, and as a consequence of this is, you raise this expression to the dth power, you see that gives you a phase factor of 1, irrespective of what the state X was. And so this means that Z to the dth power is also the identity. A definition based on these operators, a definition that we are now making, is a definition X of Q. This is just X raised to the power Q, and Z of P, which is just Z raised to the power P. Okay, I have a little exercise for you now. Based on these equations, can you compute the commutation relations of X and Z? Yeah, if you've done that, you can, it's a straightforward but useful implication. You can do that too. Okay, somebody has an answer? If you have an answer, can you please raise your hand?
I have some rubbish.
Some rubbish. How do you know? Which test does it not pass?
Difference between applying the operators in one order minus the second order equals exponent times the state times exponent minus 1.
Aha, and why is that rubbish?
Should look beautiful, I think.
Hmm?
Should look somehow beautiful afterwards. And not.
And does it not? Okay, so you have two exponentials. And from what I hear, they largely cancel.
One is factored out after the difference, the state is factored out, and in the brackets, e to the power I to p over d times q times p minus 1.
I'm not sure I could quite parse it. And from what you have, I mean, you did apply it to specific states. But from what you have, can you kind of, maybe what you have holds for all states, so can you maybe write down an operator relation from what you have? Huh? Just a relation between for x and z. So something along the lines of x times z is z times x times a factor. Good. Okay. Good. We have an answer. One answer, maybe close to an answer elsewhere. So the solution is Zx is xz times omega with omega e to the 2 pi I over the dimension. So let me, yeah, so that's it. And yeah, so once you have that, the answer to that follow-up question is rather easy. Yeah, so let's just so we recall. So this is z to the power p, and this is x to the power q. Now you're exchanging the order. So you're taking each of the pz's and move it by each of the q axis. Every time such an exchange happens, you get the phase factor of omega. So for every z here, you get the qth power of that phase factor. You get that phase factor q times, and you have p of these z's here to move to the other side. So you get this phase factor omega to the power p times q. Yeah? So that phase factor is omega to the p times q, where omega is defined in this fashion. So we will use this factor a lot of times. Okay, so this was not just some random exercise that I asked you to do. Really, really, really very many things that we have to discuss now, they will go back to this commutation relation. So that's a very important property for what we are going to do here. This commutation relation that we just figured out is a very central thing for what we have to discuss here. The while operator. So that is the next step. Maybe you remember this from the discussion of the stabilizer formalism. So we did something similar back then. So these labels that we have here, these numbers p and q, they are from ZD. So this is all modular arithmetic. So these are integers mod d. Like we had it in the binary case, we had integers 0, 1, and now we are trying to construct certain operators from these. It's basically in parallel to what we did previously in the qubit stabilizer formalism. Yeah, so we have Pauli operators z to some power, Pauli operators x to some power, but these powers are now more than 0 and 1 because, well, we have more levels than 2. So there's different algebraic relations at play. Okay. And so remember that we had a discussion about phase factors as well. So in the qubit case, there was a factor of I sitting here. And now we have something else sitting here, other complex numbers than powers of I. Namely, now we have complex numbers of this form. So roots of unity, yeah, but now dth root of unity. Okay, so that's different. And so we are taking these dth roots of unity, sorry, omega otherwise. So this is just the omega we defined on the previous slide. We take it to certain powers. Yeah, okay. And let me just say two things here. So this is a very clever choice of phase in front. So this is the choice, by the way, that you first thing to, okay, let me just say why this is clever. And I mean, this will, be elaborated on next time. So it's clear. So you take a Pauli, you take another Pauli, and multiply them, or while operators, I suppose, and these labels are just adding up. So we remember this roughly from the qubit case. But the difference is that we do not have any phase factor in front. This is something that you cannot get in the qubit case, which you already know, but you may not know where you know it from. We'll get back to that. Do you know where you know it from, that you can't get this in the qubit case without a phase? Yeah, think about it. It was in one of the exercises that you got. So that was dealing with the state-dependent version of Mermin's star. I don't know, it was named as such. It was about Pauli X and Y measurements on a Greenberger-Horn-Zeilinger state. Yeah, so you remember that exercise? Yeah, so the fact that you cannot get a relation like this holding for all while operators, such a relation holding without a phase, that you can't get that for qubits, that is related to that one exercise. And we'll get to that exercise here in the lecture, actually. This is a very important exercise. Okay, anyway, so that's the point, that you get this without any phase if you make this very clever choice. And yeah, and you see maybe already that something goes wrong in even dimension. So this, in here you have modular arithmetic modulo d. So if you are in d equals 2, then 2 doesn't have an inverse. Yeah? So you already see that construction does not apply to qubits. It only applies to odd dimension. And in fact, you can show that no construction applies that would give you this in qubits. Anyway, okay, so this relation will hopefully come to life as we go. Okay, so these are the while operators, and they are just Pauli operators, x and q, raised to various powers and then decorated with phases. So with phases that make our calculations easy. Okay, and why are we doing all this? Because we want to construct the phase point operators to make the Wigner function, and they will be based on these while operators. Okay, but before we get to that, so far we were considering just one single system, and now we have many. So let's just say we have n d-level systems stacked together, then we can define while operators for these this multitude of systems too. And so now our p part of this vector now has n components instead of one, and the q part has n components instead of one. And the way we are constructing a while operator out of that is through this tensor product. Yeah, so there is a while operator for the first system that has the first components of p and q. Then there's a while operator for the second system that has, that depends on p and q for the second particle, and so on and so forth. And we tensor them together. Yeah, so this is how we construct while operators for multiple systems. Fairly analogous to the qubit case, except that it works out more nicely with the phases now. Good, and now we come to the thing. Yeah, so we have, oops, typo. So this form of the Wigner function we are inheriting from the infinite dimensional case. Remember, we had the same structure there. Normalization factor, trace of phase point operator times density matrix. So all we need to do now is to define the phase point operators. And this is what's coming in here. And the way we do it, we define the phase point operators first, or the single phase point operator for the origin of our phase space. And it looks like this. So there's again, so this is not a typo here. So we have this normalization condition twice. I mean, this normalization factors twice. And in the end, this will lead to the fact that the Wigner function summed up over all phase space points gives 1 for every density matrix row. Okay, so now what we are doing is modulo that normalization factor. We are just adding up with same phase and weight all the while operators. Yeah, so the while operators depend on these coordinates. So there's a vector space that specifies all these position and momentum coordinates, and we are summing over all of them. So that is the basis of construction. So this gives us the phase point operator at the origin, and then we are getting the phase point operators at the other points in phase space by conjugating the phase point operator at the origin under a while operator. So every while operator comes with a position, with a position and a momentum, and we take this thing and conjugate the phase point operator at the origin under it, and this gives us a new phase point operator for the position and momentum for which we conjugated. Okay, so now this is a complete definition of the phase point operator and therefore of the Wigner function. It is not a priori clear that this is a meaningful definition, and that we still have to figure out why it makes sense to define the Wigner function like this. Okay, and we'll get to that. We'll build this slowly. So that, for now, this is just a definition, and why this definition makes sense, we will see bit by bit. So now, without proof, the proofs we will do tomorrow, that part is easy, that maybe we can talk about. Preparation independence. So when we have the Wigner function of a product state, so let's just say we have 2 qubits, and so we have a 2 qubit state, which, however, is special in the sense that it's a tensor product. Yeah? So we have one state for particle 1, completely uncorrelated with another state on particle 2. Then the Wigner function, the 2-particle Wigner function for this tensor product equals the 1-particle Wigner function for the first state times the 1 qubit 1-particle Wigner function for the second particle. That matters, and we will see later why it matters, but just where does it come from? It comes from here. Yeah? So the phase point operators for multiple particles are just phase point operators for individual particles tensored with one another. So since this holds without any phases for the while operators, and the phase point operators are just sums of these while operators, the phase point operators have the same structure. So also for the phase point operators, it holds that for multiple particles, you just have phase point operator for the first particle times for the second, turns out with the third, fourth, and so on and so forth. Yeah, so this is where it comes from. Yeah? And if it holds for the phase point operators, then it also holds for the Wigner functions themselves. That is the first property that we should remember, and we'll get to later where we will use that. Yeah, okay. We already talked about Pauli operators in the qubit case, so then the Clifford gates cannot be very far. Okay, so that is an important question here that we will have to talk about quite a bit. Yeah, you mean you remember the scheme of quantum computation we're talking about right now, quantum computation with magic states. For that scheme, the Clifford gates and the non-Clifford gates are separated. The Clifford gates you do right away, and I mean the definition of Clifford operation continues to exist in higher dimension. Yeah, so we have Pauli operators, and the Clifford gates remain those that take Pauli operators into Pauli operators under conjugation. So that's completely unchanged. And so now these Clifford operators, for the Wigner function we have defined, it does a particular thing. And that property is called covariance. So the Wigner function are transformed covariantly under the Clifford operations. That's the word, and that's the equation. So we have to unpack this equation. So what we have here to the left and right are Wigner functions for two density matrices. So there is a density matrix rho, and there is a density matrix rho conjugated under a Clifford unitary. So this is the density matrix before application of the Clifford gate. This is the density matrix after. Yeah, so that is what is being compared here. And also what you see, I mean, we know this by now, that Wigner functions also have arguments, and these arguments are points in phase space. And you see that the arguments are also different to the left and right, but they are related. So you see that over here you have some arbitrary point in phase space V, and over here you have that same point in phase space, but with a transformation applied to it. And so that transformation is dependent on the unitary in question, but it is something that acts on the phase space. Yeah? So this action of this transformation will take the phase space point V to another phase space point. Okay, so you are reducing the update, and that's really the upshot. You are reducing the Wigner function of the updated density matrix to the Wigner function that you had before the update. All that happens is that these points in phase space are shuffled around by the action of this transformation. And this transformation has a very simple structure. It is an affine symplectic transformation. In particular, it is a linear transformation. Yeah? So it's just a matrix acting on that vector. Matrix with a particular structure. Okay, so this is covariance. And in pictures, it is something like that. So, so let's think of a Wigner function that's just a peak. That's kind of a simple thing. It is not a physical state. So that does not correspond to a proper density matrix. It corresponds to some operator, but that operator would not be positive definite. Would not be positive definite or positive semi-definite. It would have negative eigenvalue. So that's not a proper quantum state. But it is, I mean, all these peaks, they are a basis for us to expand Wigner functions in. And so it makes sense to look at them. Okay, so yeah, so let's see what a Clifford gate would do to such a peak. Well, it would just move it over. It would move it over to some other location. But the peak would remain a peak. So the Wigner function wouldn't change in its shape. Yeah? A peak remains a peak, just the location changes. So that is the implication of covariance for us. Yes.
You said before that the phase-space coordinates get shuffled around.
Yeah.
So is LU a permutation or?
It is a linear transformation that preserves the commutation relations. So if you, we haven't discussed it here in the odd dimensional case yet, but in the qubit case, we identified the symplectic structure. Yeah. So recall we also had a form, quadratic form that would give us the exchange, the sign of the exchange. The sign of two Pauli operators under exchange. And here, I mean, we've already seen in this little exercise, the phase that you get under exchange is of this type. Yeah, and that property, the sign under exchange, it has to be preserved under such transformation. So it's a linear transformation, and it has special properties that it preserves such exchange phases. So that's the second property. Third property. So positivity is preserved under measurement. So what do we have here? So again, we are comparing two Wigner functions, but this time it's not the unitary that's, yeah, so for two different quantum states. So first quantum state is whatever it is, and the second quantum state is that state with a projection applied to it. So what we have measured here is one of these while operators, yeah? So given by a label A, and there's a measurement outcome S now. It's not binary anymore. Remember, we have D-level systems, so every while operator that we measure has D different outcomes. Okay, and that's the outcome. That is the label that specifies the operator. Okay, so there is the outcome of the measurement, and there's the post-measurement state. And that post-measurement state is given here. So we have the density matrix prior to the measurement sandwiched between the projector corresponding to the measurement left and right. So this is the Dirac projection postulate. Remember that is how a measurement acts. Okay, so we have the density matrix before the measurement and the density matrix after the measurement. And so now the statement is, if the Wigner function, if the density matrix, if the Wigner function of that density matrix was already positive, I mean non-negative, so that is it never dipped below zero, then for the density matrix after measurement, the same holds. So non-negativity of the Wigner function is preserved under measurement of the while operators. Okay, so that's also a property that we need to prove. I'm just kind of giving you an overview of the structure of the argument today. Yeah, that holds. Okay, and we can in fact say a little bit more. Not only, so now we apply what we just had to a special Wigner function, namely just a peak that is concentrated on some point in phase space, and now we just kind of sandwich that thing with projectors to the left and right, and we ask ourselves, what is the Wigner function that results? And that will also be important for the proof later, that we know that structure exactly, and it is this ridge here. Okay, so previously we had a point, now the resulting Wigner function in gray has support on a line in phase space, and it has the same height everywhere along that line. So it spreads in some direction in phase space. And after the measurement, you have the same height everywhere. And so, so it's basically randomly located. Your system is basically randomly located in one of these points in phase space after the measurement.
Is which always parallel to an axis, or can this be at any angle?
Yeah, okay, yeah. Good question. So I did not speak about the orientation of this line, and it depends on the observable that you measure. Yeah? Different observable, different orientation of the line.
But is it always like parallel or orthogonal to the line of the observable we measure, or can this be more complicated?
Yeah, so that's something that follows straight from our construction of our Wigner function and the Dirac projection postulate. Okay, so remember, the post-measurement state is always an eigenstate of the measured observable. Okay, and so if you measure a Pauli operator, post-measurement state has to be an eigenstate of that thing. So when you apply this Pauli operator now in a unitary fashion, you should modulo phase factor, sign factor, you should get that very same state. Okay, and so the Wigner function should also be invariant under action of that Pauli operator. And so on the Wigner function, the Pauli operator acts by conjugation. And so now let's go back to our definition of phase point operators. So remember, so the way it is written here, so the phase point operator at a certain location you get from applying a Pauli operator to the phase point operator at the origin. So the upshot of this is that if you conjugate a phase point operator by a while operator, or generalized Pauli operator, then you're moving about in phase space. You're moving to another location. Okay, and so now remember that for our situation at hand. Okay, and so now take this peak, this particular Wigner function, and conjugate it by a Pauli operator. So we have just seen that does translation. Yeah, translates into some space, some direction in this space. And so now do this with the Pauli operator you have just measured. Yeah, so by the Dirac projection postulate, this translation should not change the state, therefore shouldn't change the Wigner function. And so the direction of this ridge is precisely the translation under that Pauli operator. So that Pauli operator that you have just measured gives you the direction of this ridge, namely that ridge, remains invariant under that translation. Okay, good then. I think we are getting there for today. Yeah, and so this is now the proof idea. How we are using all these properties to show what we had to show. So let's maybe try to remember what we wanted to show. What we wanted to show was that negativity of the Wigner function is a precondition for quantum speedup. And the way we are going to show it is that if there is no negativity, then from that follows that we have an efficient classical simulation, hence no speedup. Okay, and we provide the existence of the classic, we show the existence of an efficient classical simulation algorithm by providing the algorithm itself. So it's a constructive proof. And the simulation algorithm goes like this. So first, so it's a repeated sampling algorithm. So in the first step, we have our magic state, and remember that's just the tensor product of a bunch of states. And by assumption, the Wigner function is now positive. So that means we can sample from it and get a phase space point. Yeah? So the phase space point is just a matter of sampling from that distribution. There's a caveat here. Sampling and efficient sampling are not the same thing. Yeah, so that there's a gap that we need to fill in later. So I wanna make this clear, that just because we have a probability distribution to sample from, that doesn't mean that sampling is algorithmically efficient. Yeah, so these are two different things. I so far said, okay, we have a probability distribution, we sample from it, but we have to show that it is efficient as well, algorithmically efficient. Okay, I think I can, I fit it in a minute. So let's assume we have efficiency. I talk about it later. So then come the future, the further steps. Okay, so this is the first sampling, and now for every step in the algorithm, we sample some more. Yeah, so there's two possibilities. So the next step in the algorithm could be a Clifford gate, or it could be a Pauli measurement. If it is a Clifford gate, well, then we use covariance of the Wigner function under Clifford operations. And so we've just seen covariance means that, well, our point in phase space is just kind of shuffled to some other location in phase space. Okay, so that's easy to track. Yeah, so we also saw that this is by a linear transformation, linear symplectic transformation. So that's going to be easy. Yeah, so linear algebra on a small dimensional Hilbert space, we can do that. Pauli measurement update. So this is the ridge business. Yeah, so this is where are we starting out? We are starting out here. So then we have this ridge in phase space now. So probabilistically, with equal probability weight, we are moving to one of these points. Yeah. So we just have to generate a random number from 0 to d minus 1. Assume that is viable, feasible thing to do. I think it is. So then we also know the update under Pauli measurement, or on the measurement of a while operator. And so now I can alternate between these two steps until I am done with my algorithm. So I can just kind of simulate it step by step. So that's the big picture. So that is essentially it. So there is one more thing to say about the first step. So I said we're dealing with a probability distribution. Wigner function is positive, then it's a probability distribution. So far, so good. But that doesn't mean that it is efficiently sampled from. So these are two different things. The possibility of sampling doesn't mean that sampling is algorithmically efficient. For that, we need some more. And so for that, we need a fact that we previously saw. So let's see. So we have our initial state. Our initial state is a bunch of magic state. Oh, well, actually, it will probably be a, yeah, anyway, yeah, it's a tensor product of magic states. So the important thing is we have the tensor product structure. And so this means by the property that we described, remember the Wigner function of a tensor product of states was the product of the Wigner functions. Yeah? And so this means the Wigner function of the magic states is the product of those Wigner functions. Yeah, so it's the Wigner function, okay, it has arguments P1, Q1, times Wigner function for the state M, Pn, Qn. Okay, and now, because of the assumption of positivity, these are all probability distributions. And so now, no matter how large this system is, I can now sample from these portions individually, and that's easy. So no matter what the Wigner function looks like in detail, this is a system of dimension d. Its size is independent of how many such particles I have. So that, yeah, so in the scaling sense, that positive Wigner function is now easy to sample from. And so I get the first coordinates in the first step of sampling, and then all the remaining coordinates of my position and momentum from analogous steps of sampling. So I have to do n times a very simple sampling task. Yeah? And so the cost of this process is some constant times the number of particles, n. And that is a very efficient scaling in n. Yeah? So that sampling process is not only possible because it is a Wigner function, happens to be a probability distribution by assumption, but also because of this tensor product structure, which translates into this product structure, is also algorithmically efficient. Okay, so that was that little tiny bit that I wanted to fit in for the first sampling step. Okay, and so, yeah, so that is it. So this is the broad outline of this theorem that negativity in the Wigner function is a precondition for speedup. Okay, and so that's the end of the class today. Okay, and what we will do tomorrow is to fit in the details of the proof. So, and what will that be? So that will be that the Wigner function we have defined is indeed Clifford covariant, and that it is indeed positivity preserving under Pauli measurement. So these are basically the main things we still have to show. And then maybe we have a little bit of time of talking about why all of this breaks down for qubits. Good, so that is all for today. Thank you.